Okay, let's continue to find volumes using a method called shells. And I'm going to, in this short video, find two volumes, both of which are going to be for relatively easy two-dimensional regions. Okay, so let's go ahead and get started. Now, it looks really complicated, but the very first equation, y equals x minus 1 times x minus 3 squared, I'm going to use that to graph the function. And then just to save time, I already multiplied that out for you. So if you multiplied x minus 1 times x minus 3 times x minus 3, we would get x to the third minus 7x squared plus 15x, minus 9. We're going to need both versions of this first formula. Then we just simply have a y equals 0, which is just a horizontal line, easy peasy. And then we have our axis of rotation. Okay, so let's start by drawing a picture. Again, I'm going to use this, let me highlight it in red. I'm going to use this first version to draw the curve. So this is going to be a curve that hits the x-axis at positive 1, and it hits the x-axis at positive 3. Now I can see from the multiplied version that this is just going to be a disco curve. So I know this is then going to be a curve that just looks roughly something like this. It passes through 1, but bounces off of 3, and goes up. Then y equals 0, again, kind of a tough one to draw. It's actually the x-axis. So the two-dimensional region we create is this. Okay, now the rotation we want to perform is about the y-axis, so I want to rotate it this way. So I'm going to get a mirror image on this side, and we're just going to kind of get this mirror imaged hump over on this side. And then I'm just going to do the best I can to make that look three-dimensional. So I'll have a hump here, and I'll have a hump here, and then we're going to try and make this look three-dimensional. All right, so if anybody knows what a bundt cake is, that's the shape I'm going for here. It's supposed to look just like a bundt cake. Okay, now the important part to get yourself started on any of these shell problems is to understand which axis we're rotating around. Here we're rotating around the y-axis. Please refer back to your formulas if you need to. Because we're rotating around the y-axis, to calculate the volume then, everything's got to be in terms of x. It always has to be the other variable when we use shells. Okay, and so our formula then is going to be the length, width, and height of every one of the layers of paper towels around this weird bundt cake. Okay, now what are the limits of integration going to be? Well, you notice that the innermost layer of paper towels would be located at 1, and the outermost layer of paper towels would be located at 3. So we're just going to have layer after layer after layer after layer after layer in between 1 and 3. And then the rest of the problem, we need the length, and I've given you the formulas for the length. That's going to be 2 pi times x. We then need the width of every layer, and in this case the width is going to change vertically. So notice the widths of the layers are going to be verticals. Okay, and do we have an equation that looks like y equals, you bet. We got it right here, y equals. And now I'm going to choose to use this form because if I chose the original form, I'd have to multiply it out anyway. So I'm going to choose the multiplied version of the function for the width. So that one's going to be x to the third minus 7x squared plus 15x minus 9. And finally, the height, as I've already mentioned, because we're using the y-axis, the height then has to be the differential with the opposite variable, so dx. And that then would give you the complete setup for the volume. Okay, feel free to pause the video if you want to take a closer look at that. Otherwise, I'm just going to move forward with the actual integration. I'm going to start by factoring out 2 pi and distributing the single x inside. So x times x to the third, x times 7x squared, x times 15x, and x times negative 9. Now it's easy to integrate just using power rule 4 times. Add 1, divide by the new. 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 Then we'll be F-ticking from 3 down to 1. The only term that has some simplifying is the 15 and the 3 could cancel, leaving you with 5. But otherwise, we're just going to be stuck working with some ugly fractions. Again, I'll just factor the 2 pi out front. Now everywhere I see an x, I've got to put in, I've got to put in a 3. All right, so let's see, we'll have 3 to the 5th over 5, so 243 over 5, minus 7 times 3 to the 4th over 4, so 7 times 3 to the 4th over 4, so that'd be 567 fourths, and then 5 times 3 cubed, so that's going to be 135, and then 9 times 3 squared divided by 1, that would be 81 halves. Now everywhere I see an x, put in 1 to the 5th over 5, minus 7 times 1 to the 4th over 4, plus 5 times 1 to the 3rd, minus 9 times 1 squared over 2. Okay? And because of the crazy fractions, I'm going to choose to go with decimals. Feel free if you'd rather go with fractions, that's totally fine. But I'm going to add and subtract 243 fifths minus 567 fourths plus 135 minus 81 halves. Let's see what I screw up there. I have a typo somewhere. Let's see if I can do that. Nope, I screwed something up. Sorry about that, guys. I must have screwed up a little arithmetic there somewhere. I'm going to have to try it again. 243 fifths minus 567 fourths plus 135 minus 81 halves. See if I got it this time. Yep, I got it okay. So this first one turns out to be 1.35. The second one is 1/5 minus 7 fourths plus 5 minus 9 halves. And if I punched okay there, again, feel free to double check me. I believe I got negative 1.05. A little bit more room. Let's see, these two negatives make for 1 plus. So I'll end up with 1.35 plus 1.05. And we get 1.35, so that would be 2.4. And 2 times 2.4 would be 4.8 pi cubic units for our volume. And like usual, I'll try and get this all on one page. If anyone wants to pause the video and take a close look at that one. Okay? Alrighty. And I've got one more that I'm going to call easy off to the side here. So let me slide over, enlarge the problem a bit. Okay, so one more, and this one's going to be fairly easy. Again, we'll start by drawing a picture. Y equals x cubed is just our basic disco curve. Y equals 8 is just a horizontal line through 8. And x equals 0 is just a vertical line through 0. So the two-dimensional region that we create then is that one. All right, it's going to be that region. Okay, now the axis of rotation this time is the x-axis. So we're going to rotate that shape around the x, which means we're going to get a mirror image down below. And then I'm going to do the best I can to make this look the best I can, at least three-dimensional. Make that a hair smaller. So let's see how I can do. So curve this way. Can't see that curve in behind, and you could see the whole top, let's say. So again, it's going to be kind of a strange looking funnel shape. But the key, since we're rotating this about the x axis, we're going to find the volume, and everything then has to be in terms of y's, the other variable. Okay? So the limits of integration will be what? Well, the innermost layer of paper towels is going to be located at y equals 0, and then we're going to go layer, 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 all the way to the outermost layer at y equals 8. So we're going to be integrating from 0 to 8. Again, the parts that we need to talk about are the length, the width, and the height. Okay? The length is going to be 2 pi times y. That's just from our formula. Please look back in your notebook. The width is going to vary. The width of the layers, they're going to, in the center, be really, really short, then get longer, 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 longer. Okay? But in what direction are all these widths? If you're looking at the picture, in what direction are all those widths? They're side to side. And if they're side to side, left and right, we need something that says x equals. Is that what we have with the equation? No, we have y equals. So what we're going to have to do is take the cube root of both sides of that equation, and so therefore it's going to become x equals the cube root of y, or if you prefer, y to the 1/3. So the width then is going to be y to the 1/3. And then the height is going to be the differential. In this case, when we're rotating around the x-axis, that's going to mean the differential is dy. Okay? And that then would be the complete setup for our integral. And now I'll just take a few minutes to do the integration for you guys. Again, like usual, I'll factor the 2 pi out just to get it out of your hair. Then I'm going to multiply these two y's together by adding the exponents. 1 plus 1/3 is 4/3. Then I can integrate, that's a typo. Then I can integrate, add 1, divide by the new. So 4/3 plus 1 is 7/3, and then divide by the new. Okay? Instead of dividing by 7/3, I'm going to choose to multiply by 3/7. So this is then going to become 6 pi over 7. And then what I'll have is 8 to the 7/3 minus 0 to the 7/3. Okay? Now I know I should be able to do that first one. I think that's going to be 128, but I'm just going to use my calculator to make sure. 8 to the 7/3 power is, yep, that one's 128, and 0 to any power is 0. So we end up with 6 pi over 7 times 128. And I'm not sure if that turns out, no, that doesn't turn out very nice. And I don't think there's anything that cancels, so the exact value, not very pretty, I guess, would be 768 pi over 7 cubic units. Or if you prefer the decimal, on that one, guys, it'd be 768 times pi divided by 7. So it'd be approximately 344.7 cubic units. Okay, and again, shrink that up, or try to, so you can see the whole problem in one screen. Okay, so those are 2 more volumes by Shells that are relatively easy. I'm going to pause this video, so if you want to try some of the problems in the assignment, feel free. But I'm going to make one more video for you guys, and it's going to be for one that's going to be much more difficult, much trickier. So if you want to try some of the problems until you run into issues, until you run into trouble, but then you're going to want to come back, and probably look at this last one, the tough one. Okay? So see you in a few minutes.